Hey everyone, welcome to the class 4 of Deep Learning 2020. Now in the last video, we have learned as how to create a neural network. So what we did was we instantiated a model as sequential and then we stacked one layer next to another. So in the first layer, I had specified as 5 units of neurons and this had the activation as ReLU. And this takes the input of the shape 784. That means it takes a single dimensional vector with the shape of 784. And in the second layer, I have specified as 10 neurons and that will have the activation as ReLU. Now in the third layer, I have mentioned as 10 neurons with the activation as softmax. So what I'm currently doing is I'm defining my model as sequential and I'm stacking one next to another. That means I'll define a layer and then I'll stack that layer with another layer. Now to build more intuition as how we build this particular network, now let's consider this particular deep neural network which we see on the screen. So as we can see, this takes 4 input. So the input size I can say it has 4. And in the first hidden layer, it has 5 units of neurons. And in the second hidden layer, it has 4 units of neurons. And in the third hidden layer, it has 3 units of neurons. And in the final layer, I have a single output neuron. So using our understanding from the last video, let's build a deep neural network which looks like this. So if I'm defining a deep neural network which looks like this, then I'll have to write it as, so this time I'll write as network is equal to models dot sequential. That means it's a sequential model. And then in the first layer, so I'll write as network dot add layers dot dense. That means it's a fully connected dense network. And layers dot dense, as we can see in the first hidden layer, I have 5 neurons. So I'll write as 5. And then even for this time, I'll mention as activation is equal to ReLU. That means it's a ReLU activation function. And this will take the input of shape. As we can see, we have only 4 units as input. So I'll write as 4. Got it? I have defined my first layer in my deep neural network. This takes 4 inputs and my hidden layer has 5 neurons. So this has been completed. Now I'll add in another layer. So for the another layer, I'll write as network.add layers.dense. And in the second hidden layer, I have 4 units. So I'll write as 4 and activation as ReLU. And on the next layer, I'm having 3 units of neurons. So I'll write the same. So network.add layers.dense 4 instead of 4, I'll write as 3. And on the final output layer, we have a single neuron. So what I'll do is instead of 4, I'll change it to 1. And instead of ReLU, I'll write as sigmoid. So what I'm doing is I'm defining my model as sequential model. And then I'm stacking layer next to another. In the first layer, I have specified the input of the shape 4 and this has the activation function as ReLU. And in the second layer, I have mentioned as 4 units with the activation of ReLU. And in the third layer, I have mentioned the activation function as ReLU with 3 units. And in the final output layer, I have specified the number of units of neuron as 1 with the activation as sigmoid. Okay, so I'll just execute this. Okay, now if I display the summary, see, so it says in the first layer, I have 5 units of neuron and the total number of parameters is 25. And in the second layer, I have the 4 units and the total number of parameters is 24. And in the third layer, I have 3 number of units and the total number of parameters is 15. And in the final layer, I have a single neuron and the total number of parameters are 4. Like now you might be wondering how this number of parameters will be calculated, isn't it? Well, to answer that, you need to know one important thing. The thing is, you should know what happens when a data is passed into a deep neural network. Now, whenever a data is passed into a deep neuron, let's say a particular single neuron, 2 things takes place. 1, linear operation and 2, activation. Now let's take step by step. Now when I say it as linear function, What it means is like multiplication of weights vector with the input values added with bias term. So it is Wx plus C, where W is weights, X is input, and C is bias. To give you more clarity, let's say I have an input like this. So to demonstrate this, I'll write as input numpy as np and x is equal to np dot random dot rand int, values as 10 comma 20 comma 10, and let's say I have the weight matrix which is of the form w is equal to np dot random dot rand n, and this is of shape 10. So after creating, if I display x, it looks like this and w would look like this. So x is an numpy array which is of shape 10, and this has the random values distributed like this. Now when I say it as linear operation, what it means is like it will multiply the weights vector with the input vector, and then it will add the bias term. For that understanding, let's say I have the bias term C as 3. Now the way this resultant value will be calculated is like this. So to just give you the clarity, I'll write O is equal to, I'll do the list comprehension. So I'll write as W in multiplied with X in plus C for X in comma W, for W in comma X in zip of W comma X. So what I'm doing is I'm getting the individual values from W and X, multiplying it each other, and then adding the bias term. In this case, bias is C. So after this, if I print the value of output, so this is the output that I get once I perform the linear operation. Now after performing the linear operation, the next step which I perform is activation. So if you see the deep neural network which I have mentioned, in the first 3 layers, I have mentioned the activation as ReLU. What it means is like the ReLU activation function would look like this. It just takes the maximum of 0 and the value. So if the value that I have is more than 0, then I'll consider that particular value as the output. If it is less than 0, then I'll consider it as 0. That's it. So if I want to write it in a hands-on way, so for that I'll write a function which looks like this. So I'll define ReLU, and this takes an x, and this would return np dot maximum 0 comma x. That means it will just return the maximum out of the particular value which I'm sending to this particular function. So if I pass ReLU on my output value, so this is the output that I get if I pass my input into the neuron. Got it? So what it does is it will perform the linear operation followed by activation. In this particular example, I have performed the ReLU activation function. If I want to perform the sigmoid activation function, so the sigmoid function would look like this. So it is calculated as 1 over 1 plus e power minus z. So in the same way, if I want to implement the sigmoid, I can write it like this. So def sigmoid of x, and the way it will return is return 1 over 1 plus np dot exp minus x. So this will return the sigmoid value of the output. So now to calculate the sigmoid output, that I can simply give as sigmoid, and then I can pass the value that I get from the linear operation. In this case it is O. Okay, so I'm getting an error. Okay, I'm getting an error because the data which I'm passing is I'm getting this error because the data that I'm passing into this particular sigmoid function is a list. So I'll just convert it into numpy array before passing. So I'll just write as np dot array So I'm passing it as, I'm converting it to numpy array before passing to sigmoid function. So this is the value that I get if I perform the sigmoid activation function. So what it happens is, whenever I define any particular deep neural network, when the data is passed into the deep neural network, in each layer, it will be performing linear operation and then activation function. Linear operation is nothing but multiplying the weight matrix with the input vector plus adding this bias term. So I can say as wx plus c, where w is weights, x is input, and c is bias term. Got it? So we have now understood as what is the mathematical operation that takes place inside each neuron. Now let's understand these values that we have here. If you see here in my first layer, it says that total number of parameters is 25. Why is it? Let's calculate it. So if you observe here in my first layer, I have the input shape as x. That means in first layer, the number of x, that is number of inputs, is 4. And since the number of inputs is 4, then the value, that is the number of weights, will be 4. And in my first layer, I have 5 units of neuron. Since 5 is the number of neurons, each neuron will have its own bias. Hence, 5 is the number of bias term. So total number of parameters is equal to number of units of neuron multiplied with number of units of input. In this case, number of units of neuron is 5 and the number of value in the input layer is 4. That is, I'm sending the value of the length 4. So 5 into 4 plus 5. Hence, the resulting value in the first parameters is 25. 5 into 4 plus 5, that is number of units in the first layer multiplied with length of the input, that is 4, plus 1 bias term for each neuron, that is 5. Hence I have the total value as 25. In the same way, if I calculate it for the second layer, the total number of parameters I can say as, see, in the second layer, the number of input layers will be the first layer, isn't it? So if you see the input, the number of values or the number of input units is 5. So 5. So the number of units of neuron in the second layer is 4. So 5 into 4. So because the number of units are 4 in the second layer, then the number of bias terms will be 4. So the total will be 5 4s are 20, 20 plus 4 is 24. In the same way, for the third layer, the second layer, that is the number of units in the second layer, will act as the input for the third layer. So in this case, it would be 4 into 3 plus, since I have 3 neurons in this particular third layer, 3 will be the number of bias terms. So this will be equal to 4 into 3 plus 3, then 12 plus 3, 15. In the same way, for the last layer, the number of units in previous layer is 3 and the number of units in this particular layer is 1. So 3 into 1 plus the number of bias terms will be 1. So 4. I hope you now know as how the number of parameters are calculated in a deep neural network. So we multiply with number of inputs with the weight matrix plus we will add it with bias terms. Got it? Awesome, guys. Now let's come down. So if you come down here, after performing, that is after defining the network, I am performing the compile operation. Now inside the compile operation, I am mentioning 3 parameters: optimizer, loss function, and metrics. Optimizer is nothing but the learning algorithm, and the loss here in this case I have mentioned as categorical cross entropy. I have made use of the loss function categorical cross entropy because this is a multi-class classification. If I'm using a binary class classification, then in that case, the loss function which I'll be using would be binary cross entropy. So depending on the task that I have, I'll be making use of the respective loss function. Now the way that I'll be reaching at the best value of parameters is by minimizing the loss value. So in this case, I'll be reaching the values of best parameters by making sure that my loss will be minimized. So these are some of the basic concepts in deep neural network, guys. I hope you find this video helpful, and in the next video, let's build some more deep learning network and work on other types of problem. And again, I'm telling you, if you have any questions, reach out to me on this email ID, instructor@manifoldaIlearning.in. Thank you so much, guys. I'll see you next time.